Hey, hope everybody's doing well. We are ready to start multiple regression, which is an amazing and powerful thing. Okay, so we've been talking about simple linear regression for a little while now. Let me make this a little bigger, maybe. There we go. All right, with simple linear regression, the situation we had was what we had one dependent variable, which usually we use a y to indicate in our models. That's y. And then we had one explanatory variable, or a regressor. There's a lot of different names for this one, but we call that x. That was simple linear regression. We had a model that looked like this: y equals alpha plus beta x plus some error term. That was simple linear regression. This right here, this is the simple linear regression model. Well, multiple regression, not that much changes, but it's a powerful change. All we do is we just say, not this. We have k explanatory variables. And this one, that was the noble solitary single unitary variable, has been downgraded just to x1. It's not the x, it's just one of them. We now also have x2 now. We might also have x3. We may have many, many x's. Those are very badly drawn. Oh, come on. I just wanted to get rid of those dots, because this is supposed to be dot, 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 comma, x sub k. Sometimes called xk, but these are x's with little subscripts. That's the way to look at them. So I have a little 1, a little 2, a little 3, and there's commas, and there's a k. And where k is now the number of regressors or explanatory variables, I'll use those interchangeably so you get used to it, in the model. So we have a model. What we've done so far then is we've looked at a special case where k is equal to 1. Now we're opening our horizons. K can be very big. K is a lot of things. Now we're still concerned with linear regression. That's still what we're doing. So we're still looking at a linear relationship between y, and now instead of 1x, we're looking at y and all these x's. So this is no longer our model. Our multiple regression model. What? Nuts, tell me my pen didn't break. I don't like when that happens. Our multiple regression. I can't do that with my mouse. I'm going to give this one a shot. Multiple regression model, and then I'm going to start typing, and you guys are going to be along for the ride. Is this working? It's not working at all. Okay. So our multiple regression model is now this. Apologies, but I'm very fast with typing, so it will be useful. We're talking about a relationship between y and a bunch of x's. We had alpha and beta before. If we stuck with that, we would run out of Greek letters. Alpha plus beta x1 plus gamma x2. It wouldn't work. So what we do now is we just pick one, which is going to be beta. We have beta 0 plus beta 1 times x1 plus beta 2 times x2. I don't need the times when they're next to each other. That's what that means. Then we do plus dot 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 plus beta sub k times x sub k. Get down there, k. What's wrong with you? There you go. Now we have our epsilon for our term. And that's our model. It's so nice. Anyway, that's our model. What do we have in this? Well, we have one dependent variable. That's y. We have, let's bullet these. There we go. We have k plus 1 parameters. These are population parameters, just like we've been looking at, right? They quantify a particular characteristic in the population. Once again, that means we don't know what they are, but they're abstract concepts that we're taking advantage of. What are these parameters? These are our betas. So we have beta 0, which is the intercept term. We have beta 1, which is the marginal effect of x1, which is to say it's the relationship between x1 and y. This is one of the slope terms. we have beta 2, and then we have all the way to beta sub k. You can see there are k of them, plus 1, the intercept term. We also have k explanatory variables, or regressors, and these are just our x's. X sub 1, x sub 2, x dot dot dot, x sub k, all the x's. We also have one random variable. Wow. Come on, you kidding me? Random variable. There we go. Pop that in the middle. This is going to be our epsilon. It's our error term. It's what we've been using as an error term all along. This model is very similar to the simple linear regression model. There's not that much that's new. We have assumptions on our error term. We'll talk more about those in a little bit. For now, the one that matters a lot is that in expectation, which is to say on average, we're assuming that epsilon is 0. This means that if we want the expected value of y, the average value of y, given that we know a bunch of x's, right, it's going to be beta 0 plus beta 1x1 plus beta 2x2 plus dot 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 plus beta k xk with no error, right? That's the expected value of y. Means if we knew all the x's and we knew all the betas, if we knew all the betas, the true relationships, the true parameters, and then we knew all the x's for one particular observation, we could tell you what the mean of the distribution of y is, right? So let's imagine that y is income, and x1 is education, and x2 is age, and x3 is experience, and whatever. We could just have those three. And we knew the true betas, then we could say, well, for somebody who has 16 years of education, who's 47, and has been working for 12 years in the workplace, on average, the average of that distribution of people, the average income for a person that looks like that in those ways is beta 0 plus beta 1 times education plus beta 2 times age plus beta 3 times experience, period. This property, this makes it what we call a conditional mean function, meaning conditional on x. You can even write that like right here. The expected value of y given x, which is a little pipe there. Expected value of y given x is that. The problem is we don't know betas, right? It's the same problem we've had this entire class. It is the fundamental problem we have with statistics, right? We don't know the true population. So what we do is we estimate it. What we're going to go for is we're going to try to create an estimated multiple regression equation. Actually, I can move this up because this is actually what this thing is. And our estimated multiple regression equation is similar to what we did with the simple linear regression. It's y hat. This doesn't need to be bold. And then we're going to have b0 plus b1 x1 plus b2 x2 plus dot 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 plus bk x k. And this is, in ways, depending on how you look at it, this is a sad and hollow version of the conditional mean function that we have above, right? For those of you who are into philosophy, that's the conditional mean function is like the Platonic ideal. It's the thing that we, for those of you who aren't, it's like the perfection. It's the paragon to which this estimated multiple regression equation can only hope to strive. At the same time, if you're, look at the world in a little bit more of a glass half full sort of way, it is as good as you can hope to do with the data, right? It's great. It is leaps and bounds better than just a simple uneducated guess at what average income is likely to be. So yeah, you win some, you lose some. I think this is good. Having the power to come up with a y hat like this is really useful. So what are these? Well, as before, b0 is going to be our estimate of beta 0. b1 is our estimate estimate of beta 1, and so on and so forth. You get the idea. It ultimately means that y hat is going to be our estimated value of y given x. Now, how do we estimate? How do we come up with good estimates? Well, once again, we're gonna do the same thing we did with simple linear regression. Now, if you remember, what we used before was the least squares criterion, which says basically be wrong by as little as possible. And well, what do we mean by wrong is the question. Well, what we're gonna do is we're gonna minimize the sum of squared errors. How do we do this? Well, this is the function. It's min sum sub I yi, which is the observed value of y for observation I, minus y hat I, that quantity squared. So we're going to choose B0, B1, B2, etc. So we're going to choose these b's that will minimize this thing. Right? That y hat right there, that's a function of all of these things, right? You pick b's, and that will change y hats. Ultimately, what this will do when we pick the right b's is it'll get that. It's like a line of fit, whereas before we had a line in 2 dimensions because we were just doing y and x. Now what we have is kind of like a like a surface over lots of dimensions. I don't know how to picture it. If it was 3 dimensions, we're trying to find like the right plane that fits the points, right? So that the distance between each point and the plane is smallest. So plane, I'm using my hands, and you can't see me using my hands right now because you can just see my desktop. But picture like a flat rectangular cookie sheet or something, and there are all these points kind of on top of and below the cookie sheet, and we're kind of tilting the cookie sheet around until these distances are minimized, these squared distances are minimized. When you get to 3 dimensions out of 4, I don't even know, you're moving like a cube around, I guess. I'm not even sure. In any case, it's much easier to just do it mathematically, but even here it's a little bit hard. So we wave our hands at it, and we look at a computer output. So how do we get our b's? We use a computer. And I posted a video already on how to Excel on getting and installing the Excel data analysis tool pack. So you should get that and install it, or enable it. And then once you've done that, you should try it out. Watch those videos. There's already some Excel spreadsheets on Blackboard for those of you who are taking this class. For those of you who aren't taking this class, any data will do. You can just Google data and find something, or go to the census www.census.gov site and look at population in your neighborhood, or population by income by population size, or whatever, income by average years of education. You can do that with census data for free. It's pretty easy. It's a good experience just to get your hands dirty with some data too. So okay, so that's how we get our b's. What do our coefficients mean? Well, so what is b1? Let's just answer that. If we can answer what b1 is, it'll help kind of get an idea for what the rest of them are. b1 is the relationship. It's the slope term, right? It's the relationship between y and x1. So if it's positive, that means x1 and y are positively related. If it's negative, it means y and x1 are negatively related. We'll do some. Keep your eye out for other videos. There are already some posted, but you look at multiple regression videos, you'll see where b1 comes up and what that turns into. Okay, other stuff we need to learn with multiple regression. We can see if we can get through a few other things while we're here. One important one is the multiple coefficient of determination. Again, this is what the textbook calls it. This is what some people call it, I guess. I almost always just call this the r squared. So the r squared, what is it? Well, the way we defined it before was when we took advantage of this. We had the total sum of squares, which is SST. And we separated that out into the sum of squares due to regression, which is the part of the variation in y we have explained, plus the sum of squares due to error. Right, so this SST is the total variation in y. And that's essentially, it's not this, it's yi minus y bar squared. SSR is the thing that we just minimized. Or no, that's SSE is the thing we just minimized. That's the sum of squares due to error, which is the variation in y left unexplained after regression. And then the last SSR, whoa, all the way down. I'm not sure how that happened. Okay. SSR is the variation explained by our regression. And that is it's y hat I minus y bar. There we go. Okay, so we have those, right? We've worked on those in the past. We've calculated those. You don't have to calculate them anymore, generally, right? The way that Excel works is it gives them to you. It gives them to you in something that looks like, do I have them? No, it gives them to you. Once you have them, then our r squared looks like this. One way or another way, 1 minus SSE divided by SST. Two ways to get the r squared. Okay. Now, if we have the same number of explanatory variables as observations, our r squared would be very high, but we wouldn't know much, right? So if k gets really close to n, we get into a problem that's called overfitting the data. That's not good. That's a problem. And there's a particular problem, which is this, that r squared, it always increases as you add new explanatory variables, even if those variables are just random numbers between 1 and 100. The way that the least squares criterion works is it just fits things. It uses those new whatever noise is in there, and will fit stuff. But clearly, this doesn't mean that you're doing a better job of explaining. It doesn't mean that your model is improved at all. And so what we want to do is we want to have some measure that will penalize when a model has just more regressors for no good reason. That is where the adjusted r squared comes in. We haven't talked about the adjusted r squared yet, but no time like the present. So the adjusted r squared, which is also called the adjusted multiple, man, nobody ever says this, but it is technically what it's called. The adjusted multiple coefficient of determination. The formula for this is usually what it looks like. R squared sub a, that. And what this is it's, we don't need this to be bold. It just penalizes the r squared, oops-a-daisy, for having too many regressors. This is the formula. I'll read it out loud. It's 1 minus the product of the quantity 1 minus r squared and n minus 1 over n minus k minus 1. And what does this look? What does this do? Well, when k is low, right, k is not ever going to be 0, but when k is low, this n minus 1 over n minus k minus 1 here, this thing, it's pretty close to 1. It's pretty small. But as k gets close to, closer to n, right? If k is like half of n, for example, then this is going to be around 2, which means that this distance, right, this 1 minus r squared, this is the SSE over SST, actually. That's what 1 minus r squared turns into. Basically, it weighs, the adjusted r squared, it weighs errors more heavily. Weights errors more heavily when you have more regressors. So it penalizes the model for having more regressors. Now there's a benefit to having more regressors, which is that your r squared goes up, but now there's a penalty as well, which is that this weighting factor goes up as well. So the adjusted r squared Is this the problem? Not sure what the, there we go. So that solves that problem. Other stuff with multiple regression. Let's see. I think that's enough for now. I'll post another video that has the rest of multiple regression shortly. Thanks, guys.